Good morning, guys. Today lecture is 12. So we will learn about today hysteresis laws, eddy current laws. As you guys maybe, if you guys your major is electricity, you guys must have heard about these topics, but we don't know. We don't know exactly what is that, right? But I suggested is if you guys understand this, you guys need to know the previous lecture, okay? Because I explained the saturation curve and core magnetization curve. You know what I mean? So if you guys didn't understand that part and coming here, pass, skip to here, it's kind of not easy to understand, okay? Let's do it. So the first thing is hysteresis loss, we say, right? We see this hysteresis loss curve, right? I explain, okay? First of all, you guys look at that. I will explain from here and I will explain drawing, okay? Wait, drawing. So look at that. Here is a magnetic force, right? Outside of external magnetic force, I will say H, and B is a flux density, right? So look at that. This purple line started, and when it comes back, it gotta be this blue line. Okay, just try to understand this. Okay, so this point we say latentability. Okay, so I'll explain more about it. Let's go move on. Where is? Okay. Look at that, guys. So here is I will say H, and here is I will say B, right? So you guys see, if I increase H and B also is increase, right? But look at that. At first time, it was 0, right? And it gotta be, I will say here 1, 2, 3. Okay. So it gotta be that. This point, I will say B max. Okay, B max. And this part is a saturation. Saturation. Okay. So look at that. Previous lecture we learned about it could be I pi cover, right? In I pi cover, it could be reactance, right? This slope. If you guys did understand what I'm saying, please, try to watch the previous lecture, okay? It may be easier, to understand this. So this slope, as you can see, right? It's a sharp and less sharp, smooth, and almost 0, right here. So we can say because of the reactance, is down, so that's why current is going up, right? I hope so you guys remember this part, right? And look at that. What I wanted to explain was, so here's a magnetic dipole, right? Yeah, look at that. I will do this. You guys remember magnetic domain? So there's many of small magnets, right? I explain like randomly, like this way or this way, this way, this way. But to make sure for understanding easier, I will, draw this only 2. Here's okay, N, S, okay, S, N. So I will say here's N, S. Look at the guys. So which means this 2 is H, external magnitude dense external flux magnitude, right? We could say this is I. I will say just current. Look at that. This is a steel core, and we winding with the coil. Okay, current is here. So this is I'm explaining here, right? So look at that. If I current, I gave a current in the coil. This magnetic dipoles move. Look at that. Move, 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 right? And the other part also move, move, move. We say this is a part is a magnetic uh, flux maximum here, number 3, right? And this point is we say saturation. This is almost a review, right? So look at that. The matter is, guys, look at that. Okay. When we decrease this H, as we expected, it gotta be, look at that. You can see, it gotta be like this. We thought it gotta be written back like this. But actually, it didn't. That's why we say history CS loss happened. Look at that. Which color is better? Maybe this color. Yeah, look at that. But what happened is like this, right? So what happened? Between them, there's a gap, right? Even the H is 0, but there's a flux is exists. You guys see? Okay, let's share this. I explain to you guys this. Look at the here. What I draw is now here. Look at the retentability point here. B. What I draw is right. Even H is 0. There's retentability, which means simply just remained some fluxes in the core. In the core. You know what I mean? That's it. And look at that. You guys see? Here's curves, right? Understand you guys as well. Okay. Sorry. Okay. Guys, look at that. So because of the loss, loss, it cannot be, come to the here, right? I will say. So this area, inside of this area, we will say hysteresis loss, this area, what I, make with a red part. Look at that. You guys can see. As I said, here's two type, magnetic dipole, right? So what I wanted to say is, look at that. When it goes this is 3, okay, and this is I will look. Okay, just to say 3, 2, 1, 0, okay, 3, 0, 3, 0. Look at that. So 2 is here because it's moving, right? 2, 1 is here, and 0 is here, right? But what happened is when it turned back, it's happened, loss. It's not enough energy to come back here. So it gotta be like this. You know what I mean? not enough. Because of loss, it cannot be reached here. You know what I mean? So that's why we say history loss happened. And history loss equations, you know, try to get the area, what I showed. Look at that here. The equations purposes, you know, this area, they want to know how much is it. That's it, hysteresis. Okay, guys, let's move on. Oh, and you guys can see here 1.6 here. Because generally we use 1.6 here because there's a I will explain more about eddy current, but we, you know, there's a pure steel core, right? Pure steel itself, but because of the reduced eddy current, we add something material like something resistor. So we generally use Si, you know, chemically. So silicon Si. So that means that because of the silicon Si, it gotta be 1.6 here. Okay, let's move on. Oh, look at that, guys. This is eddy current. Eddy means, you know, you guys know, right? Eddy means. But yeah. Hey, look at you guys. Try to understand this picture. Look at that. We say this is laminated, right? Because look at that. If this is good example. Look at that. You guys can see here. This is the steel core. But look at that. Steel core. Actually, you know, in the transformer, what you're saying. Look at that. This is thicker, right? But actually, if you see more specifically, it's kind of separate. I mean, like a laminate, right? Thinners, you know, sheets accumulate, and makes this. Oh, this is good example, right? This is looks one, but actually, it's thin stuffers, you know, laminate the cores, really thinner. Because why we make it thinner? Look at that here, guys. I'll explain about it, but try to understand the equation. Okay, look at that, which means that this T is thickness. Okay, thickness, and this P is resistor, not just resistor. Oh yeah, the course resistor. Okay, so that's why I will explain about this part. So which means, you know, you guys can see this is proportional here, right? So if the thickness is, you know, bigger, more eddy current happens. So that's why we need to laminate it first. And because of the resistor is non-proportional, so that's why, you know, we need to up the resistor. Try to understand it like this, okay? Let's move on. Okay, guys can see. So first of all, try before the this is you guys can understand the like transformers, you know, core, steel core. Okay. So first of all, as you guys already know, current makes magnet field. Magnet field also make current, right? Magnet, right? So and later we will learn about the Lenz's law and Faraday's law. But important thing is the induced voltage is made when the time goes by, the flux is changed. It makes E, right? When time goes by, if the flux is changing, make it E. Okay. And Faraday's, this is a Faraday's, you know, equation. But if we add this minus here, this is Lenz's. So I'll explain more about it. Okay. But if we add if we add a minus and remove minus or add a minus, it's a really important thing to understand. If you guys did understand the Lenz's law and Faraday's law, you guys cannot understand the transformers, how it works, mechanisms. Okay. By the way, look at that. So eddy current and hysteresis is a differences is okay. Try the first. Here's a coil, right? As I said, if the flux is here and time goes by, change it, here in the coil is induced, right? Voltage is induced. But what I want to say is, look at it, coil. Coil, I said this is already made it pass. There's a one-way pass, right? But eddy current, the metal is still sheet. Look at it here. Oh, you guys think this is shape is square, so there's a one way. No, actually no, because of the square, it gotta be eddy current is like this. There's many ways they could make, you know what I mean, the path, because there's only one path, but there's depends on. That's a eddy current. Okay, so why we laminate? Because I explained this thickness is proportional to the history, I don't know, eddy current laws, right? So let's see more. Look at that, guys. For example, okay. Here's a sticker, right? But look at that. This is a coil. Is a winding, right? If I current here, look at that. Current is here. Ampere's law. You guys remember? Current is here. The flux is, fluxes this way, right? So we say here, flux, right? The matter is, here's eddy current happened, right? But here is too, this part is too big. So that's why eddy current is, too big. We want to reduce it. That's why if we laminate this, okay, sorry, my drawing skill is not good. Seem like, okay. This is box, right? So since we laminate, like what I mean is slightly, accumulate this part, which means this part, eddy current is, look at that, small eddy current, small eddy current, small eddy. That's it. That's why we, laminate this sticker to reduce the eddy current. Okay, and as I said, 1.26, maybe where was it? Yeah, 1.6. Yeah, here, look at that. 1.6. As I said, because of we add from the pure steel, we add something to reduce the eddy current. That's why. As generally we use SI, we add silicone, right? That's it. And try to understand them. Look at that. Maybe next class I will explain more about further more about this. So this equation, look at the eddy current is proportional. The frequency is to 2. You know what I mean here? Instead here, look at that. Hysteresis is just a frequency proportional. Okay, I'll explain more about it. Yeah, today lecture is done, guys. Have a good day.